determine axial magnetic field produced by a current in a circular loop. For this, we have to consider a circular loop. Let's consider here a circular loop. Here, through this circular loop, I amount of current is flowing through this circular loop. Here, O be the center of this circular loop and capital R be the radius of this. This whole circular loop is in a plane. That plane is xy. And a third axis where we have to determine the axial magnetic field is perpendicular to both the axes x and y. Therefore, Z point lies on this. To determine the magnetic field of induction, we have to consider a point P. This is the point P. This point P is at distance Z from the center O. To determine the magnetic field of induction, we have to consider the small element dl of this circular loop. This is at a distance r, that is radius of this circular loop. This dl will be at a distance small r from this point P. We have to determine the magnetic field of induction at this point P, which is dB. This resultant magnetic field is divided into the two parts. One is dB perpendicular, dBz along this z-axis, and another one is dB perpendicular to this dBz. Now, we have to determine the magnetic field of induction. The magnetic field of induction at point B will be dB, and that is dB is equal to mu 0 upon 4 pi I dl r upon r cube. Call this equation number 1. This is the magnetic field of induction at this point. Now, from this diagram, we say that if here this is the angle created at this point is theta. If this angle is theta, this angle is also theta. Now, from this triangle, we use the Pythagoras theorem. According to the Pythagoras theorem, this r square is equal to z square plus r square. Here we write r square is equal to z square plus r square. This is the magnetic field of induction. dB, we substitute into that equation. Then the above equation, into this above equation, we also substitute dl dot r will be equal to dl r. Then this above equation becomes dB is equal to mu 0 upon 4 pi I dl r upon r cube. Now, from this equation, this one r will get cancelled, and here we got r square. Then the corresponding equation becomes dB is equal to mu 0 upon 4 pi I dl upon r square. This is the magnetic field of induction. Now, instead of this r square, we substitute r square is equal to z square plus r square. Then this equation becomes dB is equal to mu 0 upon 4 pi I dl upon z square plus capital R square into this equation. Now, this is the magnetic field of induction, and this magnetic field of induction is along the center of this circular loop. Now, call this equation number 2. Now, from this equation 2, we say that the magnetic field dB is equal to mu 0. At this time, this magnetic field of induction due to the dB is divided into the two parts. One is dBz and another one is dB perpendicular. If we calculate dB perpendicular over this whole loop, due to the symmetry of this diagram, this dBz, dB lambda, dB perpendicular magnetic field cancel out each other. Then there is only one magnetic field of induction that exists is dBz, and that dBz will be equal to dB into dBz into dB into cos theta. Now from this diagram, we determine the value of this cos theta. Cos theta will be equal to this R upon R. We substitute this value into this equation. Also, to determine the magnetic field of induction over this complete area, we take the integration of this dBz will be equal to Bz. That is the magnetic field of induction along the z axis, that is axial magnetic field, will be equal to dBz, and we substitute dBz is equal to dB. dB is equal to mu 0 upon 4 pi I dl upon z square plus r square. Now into the value of this is cos theta. Instead of this cos theta, we substitute r upon r. At the next step, here we substitute capital R upon small r. Instead of this small r, again from this Pythagoras theorem, we substitute, which is equal to mu 0 upon 4 pi I dl upon z square plus r square into r upon z square plus r square raised to half. Therefore, the total magnetic field of induction at this point will be equal to dB is equal to dZ is equal to mu 0 upon 4 pi I dl r upon z square plus r square bracket raised to 3/2. Call this equation number 3. Now this is the magnetic field of induction. According to this, if we determine the integration on both sides, we have to take integration, and integration of this dl, that is integration of this dl is equal to 2 pi r. The value of this 2 pi r will be equal to mu 0 upon 4 pi I into 2 pi r into r divided by z square plus r square raised to 3/2. At this time, we say that this pi will get cancelled. Here, these 2 ones are 2 2s are. Therefore, the total magnetic field of induction at this point will be Bz is equal to mu 0 I r square upon 2 into z square plus r square bracket raised to 3/2. Call this equation number 4. This is the magnetic field of induction at this point. Now, here we have to discuss, this is the magnetic field of induction, which is equal to Bz is equal to mu 0 I r square 2 into z square plus r square bracket raised to 3/2. Here, this is about the axial magnetic field produced by the current in the circular loop.